Hopefully you're a technical audience, and if you're not, you might be able to follow along. I'll try my best to make it as clear as possible because good technical explanations don't need jargon. You just really need to spend a lot of time getting the points across, and you do not need to dive into technical jargon. So basically, you're a developer, you're like, blockchains, I hear that a lot. It makes me want to vomit a little because I hear it that much. What really is it? How can I work on it? Why is it interesting? And where did it come from, right? So we're going to try and answer a lot of these questions and talk about the general systems being used in blockchains. A little bit about me. My name is Chang. I am an independent consultant, and currently I'm working with Consensus to figure out how do we make this industry less bad, because it's a lot of bad stuff happening, right? And how do we really just tighten the belt up a bit, raise the standards, have technical excellence all around, and products that have a shot at being real products in the world. And that's really important to me. Cool, so we're just gonna go over the big picture of things, the proving systems. You might have heard of proof of work, proof of stake. What is that stuff? What does it look like technically, right? We're gonna cover that stuff. Data structures, how do we move transactions around in a blockchain, in Bitcoin and Ethereum in specific, and also what are blocks and what do they look like? Networking, how does stuff hook up, and computation, what can we compute on a blockchain through transactions, etc. And maybe if we have time, we'll digress into some other projects that may be interesting in the space. But it's just really important to understand the fundamentals of the technology, the data structures, etc. I think there was a Fred Brooks quote that says, if you show me your flow diagrams, you can get lost in it, right? But if you show me your data tables, then I won't need the flow diagrams anymore, right? So really getting at the heart of the matter, seeing where the data lies and how it moves around, that's pretty key. Cool, so blockchains are just databases, and they're pretty horrible databases at that. If we compare a nice Postgres database with blockchain, right, we see different consistency models. Postgres has strict consistency modes, meaning that if you need that database to just commit things to disk and be comfortable there and be very secure that it's over there, then it'll do that for you. Blockchain is eventual consistency methodology. It uses a gossip protocol to kind of talk to the peers until everyone has the same agreement on truth. Postgres can handle terabytes of data per node, whereas the blockchain is just one big database, and every single node in the whole world shares about 150 gigabytes as of yesterday. And that's really small compared to, you just spin up another Postgres node, right? You can't do that with a blockchain so easily. And sorry, this is the Bitcoin blockchain in specific. The Ethereum one is more than that right now. And other ones too exist, but that is for Bitcoin. So I probably should have prefaced that in the text file. But anyway, point still stands. The throughput is not as good. Postgres can really comfortably handle thousands of transactions per second on sort of a commodity laptop with an SSD or something, right? The Bitcoin blockchain cannot. And there's a lot of contention about that in the community, but we're not going to get into that. So short and long of it is Postgres, a centralized single node database, very fast, and blockchain, every single node in the world belongs to this database of sorts, especially in the Bitcoin paradigm. Every so-called full node is part of the master database. And as a result, things are very slow, as you can see. So following that, you have fully trusted execution in databases like Postgres because you know everything that's running on your server. Even if you're running in a Docker container or whatever, you're very comfortable that no one's really going to be a bad actor here. I have my VPNs, I have my BeyondCorp style reverse access proxies, whatever. You can throw security on it. But if you let anyone run a database node, all of a sudden you have to shift your mindset. Like, what kind of execution can we allow here? And I kind of just made a word up. It's more like paranoid execution. We can't trust anything here. We need to add a lot of checks and guarantees to make sure this data is okay. We need to make sure there are political systems and incentive structures or whatever to make sure that we can keep this single state of truth. And that's why you get all these performance hurdles, and that's what we're going to be struggling with for the next several years. So it's important to note across all this blockchain stuff that decentralization does happen on a spectrum, meaning that you can have a really, really centralized, like a good old like IBM 360 style mainframe with databases just running on it, that one machine, right? You're gonna have a cluster of Kafka nodes, you have a cluster of Hadoop nodes, right? Or you're gonna have blockchains where anyone runs anything, right, on that blockchain as long as they are federated into the network. So that definitely occurs on a spectrum, and the recurring pattern you may see if you evaluate blockchain projects is that you really have to pick your battles. What needs to be decentralized in my system for it to be interesting and useful, and what is okay to centralize for now? For example, if you look at even the Bitcoin and Ethereum ecosystems, they're probably some of the best examples of successful blockchain projects today, yet the developer teams are still highly centralized. Now, no one really intended it for that way, and a lot of people probably prefer it wasn't, even the developers themselves. But the reality of building a software project and ensuring that everyone commits and can have changes, et cetera, that's kind of just where you have to make your sacrifices and choose your battles. Cool, so why ever do that, right? Because, again, you solve the slow stuff. Not great. When is that actually a good time to, when is it a good time to use the blockchain, right? Well, I think the best way to think about it is that you have to think about the different values that databases bring and the dimensions that they exist on. So if you really care about high consistency, high throughput, right, then you're looking at a centralized database. What does the blockchain bring if all the other dimensions are so low? Well, it brings trust in a trustless environment. And BitTorrent might be the first examples of that at internet scale around the Napster era and all this P2P file sharing, et cetera. But they also use crypto to ensure that your file chunks were okay. If you don't know how BitTorrent works, basically you have a large file, it breaks it down in a bunch of partitions, and those themselves get broken down into blocks. And those blocks are checked by the network. They have a checksum. If you edit stuff in the block or a partition, then it changes the checksum. And anyone who gets a bad block can just see that, hey, this was tampered with, I'm not accepting this, right? I reject it, I do not validate it. And because of that cryptography, you add trust and bootstrap trust in this trustless internet scary environment where anyone can get hacked. You have some degree of certainty about what's in that file. And that's why BitTorrent and DHCT were one of the reasons why it was so successful. So what's the next step after that, right? We have these nodes all hosting files, sending each other pieces of them, right? What do we do after that? What can we do? Bitcoin was the project that brought a really key innovation, which was the incentive structure on top of the technology to keep all the players aligned and keeping the database honest. So just going back to BitTorrent a bit, okay, so this torrent, the pieces are divided into blocks which go on the network, right? And they're verified, just as mentioned, just a little illustration for you. But when we have Bitcoin, we have a sense of ownership using asymmetric encryption. We have, or asymmetric cryptography, I guess is more accurate. We have more checks, and we have that incentive system, which we'll get to. But instead of trying to break down large files into blocks, we have a bunch of small transactions that can all fit together into a block. And these blocks are still the unit that we use to transfer data on the network. Transactions are transferred on the network as well, but blockchain, that's sort of what we're concerned with. So what is a block? A block just looks like this. The Bitcoin core is written in C++, and you can definitely find a lot of data structure guides around. But basically, it is a node in a linked list. That's all it really is. And it has the size, and if you're ever familiar with embedded programming or any time where you have to think about memory, then you know that the size is important to take account of. The header gives us some metadata, including those references to other blocks. Whereas we saw here, the blocks are next to each other. How do they get glued together? Well, really, we have references. And transaction count, because each block holds many transactions. So we need to know how many. And then after that, we actually have the transactions as a payload. Also, there's something known as a random nonce, which is, if you went to the previous talk here about how to build your own blockchain in JavaScript, then you might have talked about what a nonce is. Effectively, it's just a random value that can be anything you want, but we'll see how this plays into it later. Cool, so in our big distributed database where we don't trust anyone, sounds like a horrible idea, but I guess it was also a great one. Maybe that's a thin line between the two. But everyone wants to achieve the one true state. What's the state of the network? You hear about these soft forks and hard forks and everything. That's contention over trying to maintain and agree upon the one true state. And Bitcoin uses a proof of work scheme. This is the incentive model that I was talking about. This is the innovation that comes into play. Ethereum uses proof of work, soon to be proof of stake. We'll see when they release that. And just another example, because those two get a lot of the attention, but some other projects have been experimenting with other things, like proof of Spacetime, which has to do with checking if files are actually there and replicated as specified. So we're going to go over proof of work first. It was actually introduced in 1992. So one thing you'll hear a lot of programmers say is after they learn blockchain, it's like, none of the technology is new. And they're right, it's not. Like asymmetric cryptography has been around a long time, so is hashing, etc. And in fact, proof of work was actually first invented around 1992. And that's still the system, more or less, that Bitcoin runs today. And what was it used for back then? Well, apparently there was spam back then, even then. And you had to worry about that and make sure that the people that want to contact you actually weren't bots or anything. They were people you wanted to get messages from, right? So some really, really clever people invented this scheme called Hashcash. And one of the use cases for Hashcash was exactly that. So there's this number over here, 52. And essentially, that specifies how hard it is to get in contact with that email address and have it verified or some special flag so that they know you worked to get this message to that person, right? Proof of work. I want to know you did that much work to be able to get a message to that person. That's important because in economics, there are signaling mechanisms that tell maybe your buyers how committed you are. If you've ever applied to a job, then you know attaching a cover letter and really going through the motions of writing one, right? That's a form of signaling. I invested resources here to get this to you, so I really would probably accept your offer if I extended one. I'm not just applying to everyone, I really wrote one for you. Same here, like prove to me that you did this much work for me so you can get in contact with me to signal your interest, because that helps filter spam. So what is 52? Well, 52 means how many 0 bits you need in a prefix of this string-looking thing, and that's a hash. So basically what happens is this whole string keeps on getting hashed, and this is a value that's a random nonce. It keeps changing to whatever you want. So you brute force this value until these zeros, these are bytes, by the way. We're talking about 52 bits. That's why there aren't 52 zeros. But we want to see 52 0-bit prefix in order to accept that as valid. And we keep on flipping this random nonce until this whole string becomes any hash that has that prefix. It can even be all zeros, but that's pretty impossible if you look at the mathematics of it. But this means that they just kept on trying and got a hash that looks like this. What's the significance of that? How does that work? Well, a good hash function is otherwise known as a trapdoor function. And what that means is that when you change any of the parameters going into a hash function, something wildly different, almost like random noise, comes out, right? Like you just change one little bit, the whole thing changes, right? So the problem that we're betting on is that no one knows how to go backwards from like this thing to the original messages in any easy way. And this is called the inverse hash scheme that a lot of people, this particular thing, you can look that up. But basically, that means in order to get from here hash to this, there is an expected value of the number of tries you have to use to flip this random value until you can actually get that. There's mathematics that demonstrate from probability theory that if you do it a certain number of times, then after n times, you're some percent certain of getting this. So it is a function of time and trying it again, and of course computation. If your computer can spit out hashes very quickly, right, then you can get to this a lot faster. But the number of tries is pretty much it's predictable to some degree. We don't know exactly when, but like we know sort of the distribution of when, and it takes a long time sometimes. So that's important because if I see someone send me a message and they successfully solve this puzzle, right, by burning their electricity, by running all these computations on their computers, right, then I know they put in work to reach out to me, and that's their signal of interest. So that's the significance of proof of work. It didn't start with just Bitcoin. It's just a mechanism, and this soup of mechanisms that you can use to build these incentive systems. This just happens to be a foundational one in Bitcoin. So how does Hashcash get upgraded to Bitcoin? Well, instead of like this email, right? What if we could have a block containing signed transactions? Meaning if I want to send money to someone, I do a digital signature. We'll get into that in a little bit. But basically, I do a digital signature on my transfer from my account to someone else. These get collected together, put into that block we were talking about. And instead of that email, this whole block is the thing that we need to sign and do proof of work on to get those 0-bit prefixes. Additionally, in order to have a whole blockchain, things that reference each other in sort of this linear history, right? You need to reference to the previous block in a new block. So next to the nonce, maybe, you're going to have a field for maybe the hash of the previous block. So you can understand, be included in the whole chain. You're saying that this is the next block after that. That's effectively a pointer because hash collisions are quite rare with the SHA algorithm that Bitcoin uses. And also, if you win this puzzle, if you solve proof of work, you probably heard this before, but you get a Coinbase transaction. And it's basically a blank check for a certain amount of money determined by the network. That's why miners do this. They get rewarded by the Coinbase transaction, and they can put themselves as the output wallet. Cool. Any questions so far about proof of work? Went over a lot.
Silly question. How do you, if you perform all these hash functions certain times, how do you prove that it's actually, that you didn't just put a dummy value with the 52 zeros in it?
So everyone can derive that same hash because we agreed on a hashing standard, right? So they take the block data, they run the hash themselves, and then they see the zeros that they want. And presumably this is a hard problem to spoof.
So as long as several miners agree on the same result, it will be considered valid?
Yep, and if you get all the miners just to like switch their code bases off of it, right, then no more blockchain. So a lot of it is dependent on an incentive set to keep the miners just running the software as is. Yes?
Do all the miners have the exact same block, or it's whatever they recorded as the...
I see. Yeah. So
the miners could be mining different blocks.
Mm-hmm. Well, not to dig too much into it, but one piece of information that might help is that this can be anything. Like, we don't care about that. We just care about the zeros over here. So there can be multiple correct solutions. It's just a matter of who gets it first and who tells everyone, I got the golden ticket. And that gets propagated to the network. And in proof of work, the longest block wins, the blockchain wins, or they call it the highest. So whatever has the highest in the proof of work scheme will just take precedence. And if you heard of a higher one first, and someone's like, oh no, I've got one, and it's not as tall, then you say, you know, that's not valid.
So two miners, the exact same time, the exact same block with the exact same computing power, will they find the solution at different times?
They can't, you can't have two at exactly the same time because the blocks will be different. Because the
rare collision, but
the destination address for the rewards will be different.
Great. So let's see. Okay. So network difficulty. Basically, if I only wanted you to like get 1 0-bit in the beginning, you probably do that by hand. Like, it wouldn't be fun, but like you probably go in a room and like look at the math and just write it down and do it all by hand. But as soon as I add zeros, it gets more and more difficult because you have to do this more and more times to actually get one. Right? It gets very, very hard, so much that people are designing specialized hardware to do this puzzle. So why is that? Well, it's the rise in difficulty. And basically, the creator of Bitcoin decided that, 10 minutes for every block being clear, that sounds like pretty good to me. Let's figure out a way to engineer around 10 minutes a block, or else you might get too much market congestion. So effectively, if the algorithm decides that and looks at all the blocks being minted, hey, it looks like we're going kind of fast here, right? Let's slow it down. We raise the difficulty to get it closer to the target of 10 minutes. every block. So even if a bunch of miners join the system one day, over time, the system will recognize that, hey, these blocks are being minted too quickly. We got to slow it down and raise the difficulty. Vice versa, if the miners start leaving, then the difficulty starts falling. But this takes time. It doesn't happen immediately. So that's definitely something to consider. But that's how we maintain a consistent block. Yes?
Why is it 10 minutes? Is there a reason why
I don't know.
it's faster?
There might be a good reason. I don't know it.
It used to be with the speed of the internet.
All right, cool. So check proof of work is literally this. And there's a function call in there. So sorry, maybe you should have copy and pasted. But you look at the type signature. And you just have a hash, right? You have how many bits, what's the difficulty at right now, right? I omitted some stuff so it could fit on the slide. And some metadata you pass around in this function. And basically you just check did we get our target? Was it all right? Or did we fail? And that's essentially it, just checking the 0 bits. This is taken directly from Bitcoin Core. All right, cool. So proof of work has some criticism and also some benefits. And all these models have pros and cons that people just talk about for all day. But we're interested as engineers, what are these things, right? Not so much the politics yet. Effectively, proof of work is kind of like a lottery. If you have everyone, crunching their SHA hashes or whatever, and trying to get to that 0 prefix, right? It's a lot of computation that we're wasting. In fact, in order to get a certain throughput on the network, we need a lot more computers doing sort of a mainly useless thing. What it reminds some people of is high-frequency traders who just invent faster and faster, like sub-millisecond, microsecond, whatever, really fast lines, so they can trade faster. The invention of those technologies just to get your bits over to Wall Street may not have a very successful impact on society, right? So from that perspective, maybe there's a better use case for those resources, but of course there's always pushback on that. So a lot of people were like, hey, let's just make it a lottery, right? Let's do proof of stake. So instead of doing this mining activity with the proof of work, proof of stake systems are basically you have some of the cryptocurrency and you put it up as a stake. Can't touch it. It's a stake now. And every once in a while, it rewards someone from the stake pool, depending on how much stake they have in. So it's proportional. You get luckier the more stakes you have. That's not all proof of stake systems. There are some variants, and there's also something called delegated proof of stake. We won't get into that. But that's sort of the main idea that, hey, let's just pick who to reward people and who gets to build the next block. And if they do something wrong, we'll punish them. One of the biggest criticisms of proof of stake or certain proof of stake systems is that 51% attacks are possible in that you can rewrite the entire history of the blockchain if you get a majority agreement. Whereas in proof of work, that's actually not the case because you still need to do the work to catch up and be the longest block to do that. And if there are a lot of blocks ahead of you, it's you versus the computational resources of the rest of the world, right? You have to be like a nation state or something to have the economies to do that. It's basically burning electricity to pay for that certainty. All right, and one more interesting one that I said we'd cover. Let's make sure we're good on time. Cool, so proof of space-time. So instead of computation, let's have people, instead of solving these kind of useless puzzles, let's have people actually host useful data for people, and that can be the mining in the system. How do we prove that the data are actually being stored correctly? We can do so by making it more expensive to spoof the storing of data than actually storing the data. So maybe if I give you a file and I want a proof that you always store it, right? Maybe every day I just wake up like a really annoying neighbor and I call you, right? And I'm like, hey, Lex, what is bit 78 through 79 say on that file, right? And if consistently I get the right answer and I can just probe these random ranges, right? Then presumably they still have the file because it makes no sense to try and guess which one of these random ranges I'm storing. It just makes sense to store the whole file. And of course, if they answer incorrectly, then there is punishment. So that might be a theme that you see occurring over and over again with some of these evolving systems. As we reach the tendrils away from just dry computation that always produces the correct result, you bring more people involved, it does get more political. You have things like staking, which is almost analogous to land ownership by some degree. You have these punishments that have to incentivize good behavior. Very much, these are the mechanisms. It's really interesting territory because these are the mechanisms of computation that you can bridge with sort of a political or incentive layer on top. And that's why they use that word that I don't like, but it's called crypto economics. And that's sort of what they're talking about. Like, how do you combine these things to have a working system? Great, so Bitcoin transactions. Diving back into the data. So no Bitcoins really exist. You probably know that if you've seen previous talk, but if not, unspent transaction outputs are really the name of the game in sort of Bitcoin. Because I can't look up like where the Bitcoins are. Like if I have a Bitcoin wallet and there's no like one place I can query on the blockchain to figure that out. Instead, you just collate and collect and add up all the transactions that have this field called an unspent transaction output that you have ownership over and can then spend on the network. That's basically the Bitcoins that you own. And there's a lot of activity that has to happen to validate this. Cool, so fees are paid to miners to secure the network and prevent attacks. So secure the network. How does paying fees to miners secure the network? Why don't they just take the fees and run? Well, if we basically, when we pay a miner a fee, if they do the proof of work correctly, they are incentivized by the Coinbase reward and collecting all the fees to do the right thing and propagate to the rest of the network. If they do the wrong thing, even if they do the proof of work and they make something invalid, then no one accepts that, right? And they lose out on that opportunity. So those incentives really help align their behavior to do the right thing. And if you're more curious about mining incentives and like what are possible attacks miners can try to do, then you probably should look a lot around the validation code in Bitcoin Core and think a lot about like, what happens if I tweak some of these values and then my blocks aren't valid on the network anymore. There are definitely penalties there. And how are the payments moved around? There's a Turing incomplete language called script. It looks a lot like a programming language called Forth, which was a kind of an old and early language that it looks a lot like, it looks a lot like Lisp in terms of its simplicity, but it's a stack-based language and has different functionality. And of course, everything is stateless. And what I mean by that is when a miner looks at a transaction put into a block to validate it, or you look across the blocks and see the transactions, then you're able to look at every transaction as more or less of a function. And we'll get into that in a little bit. So I think it might just be easiest to go through some examples. The last point, though, is pretty important to cover before we move on to that. Basically, what are locking scripts or witness scripts or unlocking scripts? You'll hear those a lot. Well, they are use cases of the script programming language. And basically, the locking script says it locks down a transaction output and says, unless you have this the solution to this puzzle, you can't access any of these funds. And the unlocking script says, I do have the solution to the puzzle. Here it is, and it could work or not. And if you clear a transaction, then it worked. So script, let's get into a little bit. So it's like a backwards Lisp, as I was saying. If you've seen reverse Polish calculators before, then you sort of like understand how it's going, but it's like not reversed. Let me just get into the example. Basically, how does this work? 2 and 3 go onto the stack, right? And then when we push this function onto the stack op add, it pops both of its parameters, gets 5, right? Now we have a 5 and 5. And those get popped onto the stack, or sorry, pushed onto the stack, my bad. And then as soon as this gets pushed onto the stack, then we evaluate everything, run the function into optrue. So back to the locking and unlocking scripts. This is what it looks like. It's interesting because if you are familiar with functional programming, then it kind of looks like partial function application. So this is a P2PKH, which you'll see a lot if you're starting to dig more into Bitcoin stuff. And essentially, we want to check the signature and also take a hash of something with the address and understand that it's equal and verified. So the unlocking script are actually the input parameters to this function. So the unlocking script goes in front of, as input to, sort of this script. And opdupe means duplicate it, split the input, hashing and equal verify. So this, without spending too much time getting into details because we're running a little low on it, that's basically the locking puzzle piece and then the unlocking answer. And definitely check out the script documentation if you want to learn more. Some other script functions, check multisig. Instead of checking one signature, one answer to the puzzle, you can accept m of n possible answers. Pay to script is a kind of an interesting one. Instead of a wallet address that things get paid to, you can actually pay to the hash of a script of a transaction, and it'll be okay. That script can freely spend whatever unspent transaction outputs are delegated to it. Return is a way to just encode data into the transaction. Some people use that a lot. I wonder if Tyrion does. I haven't seen their stuff. And yeah, some further functions provide control flow and can be used to lock transactions. So maybe you want to do maybe you're like crypto wealthy, you want to do like a trust fund thing for your kids. I guess you can do it with script. So it unlocks on their 18th birthday, more or less. All right, great. So that's script. I'm not going to spend too much more time on that. On the Bitcoin network, all the so-called full nodes store a full copy of the 150 gigabyte blockchain as of today, and it grows linearly over time because of those 10-minute block building sessions that we were talking about. There are probably around 10,000 nodes. That number varies. It's like really hard to tell, just like how it's really hard to tell on BitTorrent how many nodes are on the network. So that's difficult. There are techniques that you can use to just sort of ping scan or follow transaction, et cetera. It's just really difficult to gauge where every node is or how many there are. That's the decentralized nature of it. They don't really report to they don't report to the man, right? So you got to figure it out. Just routing nodes forward the messages and reduce congestion. And the mining nodes actually look for things using proof of work. Now, the so-called standard node in Bitcoin does all this stuff, right? But since you see some specialization in this market, in that, of course, people have mining rigs, you have wallets that that don't hold the full blockchain. That's ridiculous to hold the full blockchain on your phone. Today, maybe it won't be in a year or two, but we'll see. Routing messages, so routing nodes are actually part of certain types of wallets. So you see some specialization of these fundamental functions turn into what you're familiar with running on the network. This is basically what the nodes on the network do. One thing you probably heard of, and it just comes up, Merkle Trees. You'd probably come up with it yourself. It's like not a super secret computer science term. It's not like NP hard. Well, some parts of it might be, but I don't know those parts. But anyway, so what's a Merkle tree? Basically, if I have like a bunch of hashes, right? I'm like, hey, how would you take these hashes and give me one hash instead of all these hashes, right? Well, you would just like maybe concatenate them and kind of hash that, and you'd get your hash back, right? I was like, okay, well, I got a tricky one for you. You know, what if I gave you another hash after that? It's like, okay, maybe I'd put it next to the hash I have now and hash the thing again, and I'd one hash that kind of represents the ancestry of all those hashes, and you can validate that. So that's what a Merkle tree is, just in case you hear it. All right, cool. So Ethereum. So we just went through Bitcoin world, and now we're starting to go into Ethereum. So script isn't Turing complete. What does that mean? That means that you can't represent any computer program. You can only do some simple things related to payment transactions, and I believe that was quite intentional, because as soon as you let programmers go wild and do whatever they want, right, then you start to have a problem because programmers write bugs, and programmers write things that, things happen that they didn't intend to happen. Complexity is really hard to decipher through. So for the purposes of a payment processing one, maybe a Turing incomplete language is good. But the Ethereum project set out to create sort of a universal computer based on blockchains. So they're like, hey, like we store values on the Bitcoin blockchain. In fact, here in return, right, we can store up to 80 bytes, right? What's a computer program when it's compiled? Well, it's just a series of bytes. That's a large number. We can just store that large number into a transaction. And that's what they did. So they have languages that compile down into a large number, otherwise known as a binary blob, or whatever, and they can put into the transactions. And the miners, the nodes, know how to run these opcodes, these binary blobs, as executables. So now you have a problem, because it's known in computer science land that it's very difficult to figure out if something is really like computable. Like, does this computation finish, right? The holding problem. So to prevent that, you need to pay gas to run your program for every operation that you do on the network. Because presumably this computation power costs money, right? So people should be compensated for running those computations. So it's really funny because like in like the 70s or 80s, right, people were really trying to write tight assembler loops, trying to figure out how do I squeeze everything out of this little Intel chip or something. And we thought we were done with that when we had all the cores and gigahertz of processing power. But now here we are again. You're really like trying to roll those tight loops to make sure you get everything out of it, because that's expensive to run on the network. And even worse, all the programs are run by every node on the network, like one big mainframe, kind of like the IBM 360, right? You could run one thing at a time. And if you wanted to switch processes, you could do that. But like it was just one mainframe, and that was the straightforward execution path, no concurrency or anything. So that's what the network looks like. All the nodes run the same code. And what do Ethereum transactions look like? Well, this is from a Python client, I think. And basically, we have the nonce again, because they started proof of work. We have the gas price. We have the start gas, how much gas the transaction starts with, and a bunch of to and fro addresses. Data, arbitrary data, including code or any kind of data structures that are built in. And by the way, the more data you want to store, the more gas you have to pay as well, because it also costs money to permanently store things to the blockchain. And we have some things for cryptographic signatures. And this is an example of some bytecode in the EVM. EVM stands for the Ethereum virtual machine, much like the Java virtual machine or Beam, the Erlang virtual machine. And what it does, it provides sort of a portable assembly that was supposed to be C, but really the more portable thing that really looks like assembly is Java bytecode if you look at it, or Beam bytecode. Basically, higher level programs compile down to bytecode, which can then run on any architecture, presumably, that you have like a bytecode interpreter on, or a runtime, so-called. And effectively, Ethereum has the same thing. The Ethereum virtual machine is that runtime that can understand these bytecodes and do computations. And it's a closed system, meaning that we can't really make HTTP calls or whatever, because that ruins your consistency of your system. Like maybe I have like a value somewhere stored, right? And I'm like, hey, pay me this much money. And the money is on my web server, right? Just go there and get that integer and use that in the transaction. That's actually quite difficult, and you get a lot of bad stuff from that, because as soon as you reach out and go there and immutably record the URL on the blockchain, right, you get a certain degree of inconsistency. Everyone might have a different view of that URL. I might have like a proxy, reverse proxy that kind of load balances people to different places or something nefarious like that. And that is not consistent, whereas we're trying to strive for full consistency in that one true state I was talking about. And these are just some more examples of some bytecode, opcodes rather. Okay, so references. If you're a developer, you're technical, you want to get through, you want to go through here. Mastering Bitcoin is definitely where to start. Just read that. It's going to go through everything, or I want to say like 60% of what I just spoke about in like a lot of detail. That's definitely the place to start. After that, everything's open source. Start tearing through the clients. And that is my presentation. I'd like to open the floor to questions. Any questions? What's up?
The basic proof of work versus proof of stake from an Ethereum perspective and the impact on the large mining community that's already been built around proof of work. So in proof of stake, let's say I have 10,000 Ether and I put that up to be a validator. Who then provides the computational power for that, right? Because as a validator, I really don't have to be a miner anymore. I'm just securing my wallet somewhere and saying I'm willing to use my wallet to bet on whether or not this block is valid, right?
So
I'm struggling with that, how that's going to work.
So part of actually being able to add a new block to the blockchain means you have to validate the block, right? And basically that means even if you're in that lottery, right? You get selected. Hey, you can make the next block. It's really easy now, right? Then you can make the block, validate it, and everyone can check your work. And if they find some defect with your work, then you get punished. Does that help answer your question?
So there's not the requirement for the amount of computational power though that's in the network today.
No.
Right? So there's the potential of eliminating all the GPU-based processing and basically being able to do proof of stake just on normal computers or on cloud, AWS or.
That's the thought, and presumably it's going to help throughput by a lot. And of course, it comes with disadvantages too. So, yeah. Yes.
So when you say they get punished, what do you mean by that?
They lose some of their stake.
They lose.
Yep. The best way to punish someone on a crypto system is to take their money. So if they have something up for stake, then you take some away, did a bad thing, and hopefully they learn their lesson. Yes.
That was exactly my question.
Okay. Great. Yes.
We talked about duty on the side attacks being possible as being the downside, but is that not possible with hashing pools or mining pools? Sorry.
It's a lot harder because let's just look at these blocks here. Just going back to these blocks. All right, we got all these blocks here, right? Each of these blocks that are basically on top of each other, right? There was like non-trivial amounts of electricity that went into computations to derive each of these blocks, right? So for an attacker to really take over the network, they have to have their computation power fight the computation power of the whole entire network because they need the longest block. The network is probably going to build blocks a lot faster than most people can, even if they're pretty wealthy attackers. You'd have to be like somewhat of a nation state or just someone with like, billions of dollars of resources ready to throw at this. Yeah. Well, we don't know. Those are questions that we can use math to approximate, but yeah, it's hard to tell. And it's as the market cap of Bitcoin gets higher, right? Then it may become a more attractive target. So that's another thing to weigh as well. Any other questions?
Is proof of stake immune to quantum computing?
So I think the immune to quantum question is like it's hard to say because we don't know what the good encryption is that can beat quantum or provide some resilience against it. I'd say that I imagine it could be. Same with proof of work if we can discover the right algorithm, right?
Actually, proof of work is an NP complete problem, which means the proof of work is immune to computing. But the proof of stake is not an NP subject quantum computing attacks.
So I'm out of my breath in terms of talking about quantum computing and NP completeness. I don't know how those two terms relate. Cool. Oh, yes.
When you are creating the transaction, then I have the private key to my wallet, right? And I'm signing that transaction.
Yes.
Could you expand a little bit on that? Like, how does that work, and how couldn't somebody just do a transaction for me?
Got it. So your wallet address is actually your public key, just encoded in a different way, right? So we know that if you have the private key to sign that transaction from the address in your public key, right, then there is a scheme that exists to let that happen. That's a general view. We can talk about the details if you want after. Cool. Well, thank you so much for coming to this room 1 instead of room 2. So appreciate it.